All right. So let me see. As I move along, let's say that it's sitting like that. So this is, if right here, the cross section would look like the circle. And let's say that this thing is 4 there, and let's say that it's 8 there, right? So in this case, it's kind of a boring example because the cross-sectional area, no matter where you are on the x-axis, is the same. It's not going to be a rectangle, though, right? I mean, what's the cross-sectional area of this cylinder?
Circle.
I know my picture's bad, but you guys see that that's like a soup can or something? Or a Pringles can, really. It's more elongated. So the area of the circle would be what? What's the area? Good. And what's the radius?
2.
2. So it'll be 4 pi. You with me? So in this case, the function that describes the area is a constant. So you can almost argue it doesn't even need a single variable, but for any given x position, that area is going to be 4 pi. You with me? Okay. So the cool thing is, if I want to get the area, if I can say, now here's like a of xi. Don't worry, we're not going to do the whole summation thing and all that kind of stuff. This is just kind of building on those same ideas. In much the same way, I can say the sum, I equals 1 to n. I can just do that same thing. Where the area I'm talking about is the area of that, and then the delta x would actually make the thickness of that. Now, considering who you're talking about here, that's not that bad. Can you guys see that would be a thickness like a coin in the middle of that, right? Okay, and you can see it better maybe here. Let's see where they're doing. They're going to do that here. Yeah, that's not too bad. Yeah, they got some irregularly shaped loaf of bread that had a rough time in the oven. I don't know what that is. So here, this would allow for the fact that the area might be different as I move along, which would be true for a sphere. So we're going to do a sphere next. Then if I apply that limit, so now I'm letting the number of little disks, so these are all going to be little disks. Is that cool? A disk would be like a coin. It's got a thickness to it and it's circular. So these is called the disk method. So if I let the number of little disks, which are like my little rectangles for area, but now to do volume, I need something that's got some volume to it, so I would use these disks. And if I let the number of disks I use go to infinity, I'm going to need exactly the right volume. So this piece would, of course, become the integral. In this case, it would be from 0 to 8, but in general, a to b, of the area function. Cool. And of course, you know that, and later we're going to apply the same idea to y in case they stand my cylinder up along the y-axis. Then I can just use the y variable instead. Okay, so for this problem, that integral will look like 0 to 8. Area is 4 pi each time dx. What's the integral of 4 pi? Yeah, that's where the 4 came from. Right, the radius is 2.
Oh, Roger.
So 4 pi x from 0 to 8. So this would be 4 pi times 8, 32 pi. Right? This is kind of silly to start here because what's the volume of a cylinder? Well, the volume of a cylinder is pi r squared h. So in this case, it would be 4 pi times the height, which is 8. So 32 pi, same thing we just got. So of course, if you have a really nice shape, just like you would if you have a triangle, I'm not going to apply integration to it. I'm just going to figure out half the base times the height. Right? So in this case, I'm not going to use integration to figure out that volume, even though I just did. I would just do the formula that I know exists. For a sphere, let's do a sphere real quick. And the sphere, I don't want to get too much away here. down there. So the thing about the sphere, and this is in general true, my sphere looks like that. And they put the origin at the middle, that's a good idea. Here's the radius, the true radius. I'm going to call this guy, I'm going to do a little different than the book. I'm going to call this some other kind of thing that the book does. Look what happens as I move along the x-axis. So whenever I come up to x point, what is it that I'm looking for it to describe for me? So from this example here, when I get to an x point, I want it to describe a disk. And in fact, just the area of that disk, right? The delta x will be the thickness that makes it a disk. So I want the cross-sectional area of this sphere at that point. And of course, if you have a sphere and you slice it, what shape will that take? Circle. The whole point now is finding the actual function that defines the area of that circle for any value of x. So what do I need to know then to get the area of that circle? Yeah, it's a little bit better up here. But I need to know this radius. I love it. So what is this radius here? I'm going to call this big ass R. Right, they call it Y, but it's going to make a little more sense to me. Call it big ass R. That's the middleman radius. This is the true radius of the shape. This is just the radius for the cross section. So what is that in terms of x? In fact, we'll do this. So what kind of shape do I have going on here? Triangle. In fact, even better than that.
Right triangle.
Right triangle. So then you know that this side is going to be the hypotenuse squared.
Minus.
Yep.
X squared.
Cool. How we doing so far? So do you see how, in general, if you have a 3D object already sitting there, you want to figure out, okay, if I go to some arbitrary x position, can I define what the area is right there, the cross-sectional area? Can I define what that is in terms of x? If I can, I just have to integrate that all along as what x changes from to. How we doing so far? Okay, so that's how you build a sphere, is you make very small circles and then make them bigger for the middle and then make them small again and you glue them all together, you got a sphere. That's one way to do it.
There's no function for creating that sphere, right?
The sphere exists on its own. We're not looking at it as if it's some function has created it. Yeah.
Can you only do half the sphere and then the other half? Right?
Yeah, you could. You just double it because you know it's symmetric. So let's go back to the basics here. I want to go for integral from a to b, cross-sectional area at any arbitrary x dx. So what is my area going to be? Here's my radius squared. And of course the area of the circle is going to be pi r squared, so I don't have to take it all the way down to r. So the area of my cross section is just going to be pi times this. Let you guys absorb. Okay. So now I just plug that in. Where am I going from to? So I've got two different ways to do it. Or I can do like you said, or I can do it straight up. How far back is this? Negative.
X squared.
No.
Negative r. Negative r.
Negative little r, right? Because it's the radius back, right? It's a sphere. The radius has got to be the same in all directions. That's beautiful. So this has to be r. So you're going from negative r to r. And you're going to add up all these little circles to make the whole volume. Okay. What's your true variable here? R is set. I don't know if I just imagined that I heard somebody say X or not. R is set. R is the radius of the sphere that I've got that I'm working with. It's not a variable. The sphere is not like growing or shrinking. So then how do I integrate this piece? Must be some reason I just said what I said right before I said this.
It's like pi r squared x.
Pi r squared x. Pi r squared is a constant. Little r is the radius of the sphere. The sphere exists. It's a basketball or a bowling ball, whatever. So I got pi r squared x minus, how do you integrate x squared?
Pi over 3, x to the third.
Yeah, good. Pi x cubed over 3. And I want to go from negative r to r.
You back up one step for me, I'm sorry.
Yeah.
Where it says A equals pi big R squared equals pi R squared minus pi X squared.
So here's big R squared.
Yep.
So all I did was plug this in for big R squared. Multiply by pi.
Right.
And if you do all this, you'll get pi r cubed minus pi r cubed over 3 minus negative pi r cubed minus negative, so plus pi r cubed over 3. So if you put all that stuff together, you'll get 2 pi r cubed plus, where am I at? Minus that, minus, there we go, 2 pi r cubed over 3. This is all detailed crap. This is just plugging stuff in, seeing where it leads. And what's 2 minus 2/3?
4/3.
4/3, all right. 4/3 pi r cubed. Bam. And that, of course, you should know is the volume of the sphere. So you can finally prove that thing that we know. Very simply. Built on knowing the area of a circle. Right? Because that's how you create a sphere. You put a bunch of circles together. So it should make sense. Adding up areas of the circles that went into making this thing should give you the volume. Okay, so I want you to realize when we integrate just a function, just a 2D function, let me see if I can say this. When I integrate something like this, x sets up how tall my rectangle is. If you use it as a midpoint, if you use it as a right, left, who cares? Because, of course, in the limit, it doesn't matter. It's going to just go whittle down to just one choice. You guys with me? X represents how tall that thing. X leads to being able to find out how tall that thing is. And it's the height that I multiply by the length to give me the whole area. So here, x, what does x by itself do? X by itself gives you the area. Right there. That's why I don't have to have like a double integral. I don't have to go there yet. You guys don't even know they existed until I said that earlier, right? A double integral would be if you want to go in the x direction and the y direction somehow, right? We don't have to go there because x by itself defines the area at that point, and then I just add it along across x. That's all I have to do. It's exactly the same as what we did before. Believe it or not. Alright, so that's one set of 3D objects that we can work with right now, is if I can define an area dependent on my x position, I can then find the volume of that thing this way. So of course, I don't always have just a 3D object sitting there for me. Sometimes I create a three-dimensional object based off of something else. So that would be the next type of thing we want to look at. And this is called solids of revolution. And I'm really upset at myself. very quickly, here's a little animation. Let's see if this loads right. Cool. Just showing like here's n equal 4, so only using 4 disks. And this is kind of cool, I can kind of move this around. So there's 1 disk. Let me take this guy out of here. 1, 2, 3, 4 disks. Do you see that? So that's my 4 disk approximation of a circle, of a sphere. And then if I take that bad boy up to 40 disks, here's 18 disks. Here's 40 disks. Now that's looking pretty spherical, right? So of course, this is the kind of thing, this is exactly analogous to, I can fill in the area under a function if I use smaller and smaller rectangles, get better and better resolution. Same thing here, 3-dimensional. And each one of those disks would be controlled by the x position or the y position, depending on how I orient this thing. Right? Looking at that, all I can think is Chinese lantern, but that's so we're going to move into this, which is kind of nifty. So let's do this. We got a little worksheet that we're going to work on later. But if I look at this, y equals square root of x. So let's see, what's it say? And what they're kind of implying here is that it goes from x equals 0 to 1. So what is it on the y-axis? What's this? 1. I love it. Square root of 1. 1. So I'm looking at that. Now here's the thing. Now that's not a volume, obviously, right? So some of you guys might be realizing that and saying, how does this apply to this? So that's not a volume. But what we're going to do with this is we're going to rotate it. And this is the thing I left in my office. Back in the spring of 2010, I taught calculus last time, and I said, man, I wish I had one of those things that you open them up. You know what I'm talking about? And now I do, and I left the damn thing in my office. Dumbass. So it's basically shaped like that, and you see that like we had one for Thanksgiving. It was a turkey, and you open the back of it. You know what I'm talking about. So here, this was like it was basically shaped like that, and you open it up, and then it's a sphere, right, or whatever shape it was. Okay, so that's what we're going to do. We're going to actually rotate this thing around. We could rotate it around. What's this one rotating around? Let's see. Does it say? Oh, here we go. Rotate around the x-axis. So it's going to rotate this way. I could rotate it around the y-axis, make it look like a wine glass, right? Here, if I rotate it, see that? You can even look at it from a different angle. Rotate around the x-axis. Makes this shape here. Nice walk. And then you can kind of move around your disc that you're using there, right? Cool, man. All right. And it's solid because of the fact that my original area, they should shade this in, but right there, I start with this area here, and then I rotate that whole area around. So it does end up being solid. It's not just a bowl. It's actually this solid thing. You guys kind of with me? Okay. The nice thing is, the computer can obviously draw that pretty well. You do not, please, unless you draw really, really well and you want to make me cry about my horrible ability, you do not have to draw that to be able to do the math. The math doesn't require some kind of rotation to be in the math. All the math cares about is this region. How would I do this? So if I rotate this thing, let me see if I can attempt it. Do what I just said I wouldn't do. It would be like this, and like that. That's not too bad. All right, so for me, that's pretty damn good. What would the radius of so if I'm at some arbitrary x, the cross section would look like a circle. In fact, anytime you do this procedure, if you rotate something around, it's going to end up looking like a circle. Because wherever that functional point is, it's going to be that same distance away from that axis. You with me? So you're always going to end up with circles, thank God. So the area will always, for this method, for the what's called the disk method, and you'll soon see something called the washer method. The idea is if I can just figure out what the radius is, I'm golden. Because the area is always going to be pi r squared. So what is the radius here? For the circle, if I'm at some arbitrary x point, what is that radius? Don't overthink it. Why did I stop there? Yeah. Right? From 0 to there, well, that's square root of x. Right? For any x, how high does it go? Square root of x, because that's where it stops. It stops on that function. You with me? Okay, good. So the radius here is just going to be square root of x.
It's long.
How we doing? So I didn't need to, and now I'm thinking about it, I shouldn't have drawn that damn thing, just so you knew you don't need to draw this 3D image. You don't. All the work I just did was really all contained in this image, in that first quadrant. And well, it's not always first quadrant, but it's just in that area they give me. That's where I can do all my math work. The rotation comes out because I'm building my circles off of what that radius would be. I don't need to draw them in. I know the radius is going to be whatever that distance is. So how do I finish this out? The volume is the integral of the areas. And I'll tell you this right now. Here's the kind of cool thing. Because I was saying earlier about the x and the y. Sometimes you have to do dx. Sometimes you have to do dy. This is a definite note. You do dy when you rotate around a line parallel to the y-axis. So you go incredibly enough, you do integral dx when you rotate around a line parallel to the x-axis. So what did we just do? We rotated this around the x-axis. It's obviously parallel to itself. That's why we're doing integral dx. Are you guys with me? Because that's one of the most difficult things to keep down when you get a little further along. This is not that bad. There's a really nice rule here, which is the general idea of which one do I do? Do I do dy? Do I do dx? And the further you get in calculus, the more stuff there is going to be to consider. So what's this thing going to look like? What am I going to integrate from to? What does x do? Let me give it away. 0 to 1. Again, I do not need the 3D image at all to be able to set this integral up. So why does it end up being 3D? Because of this. That's the part that captures the rotation. So here I'm going to have from 0 to 1. The area is pi times, what's r squared? X. Cool. And then how do you integrate that? There, I'll go ahead. So that volume ends up being pi over 2. How are we doing here so far? So the real, I really want you guys to realize, when I'm doing this, and they make a big distinction between discs and washers. What does a washer look like? It's got a hole in the middle. So how does that relate to areas? That would be a cookie cutter. I would do the volume for the outside radius minus the volume for the inside radius. So it's just a stupid disc method where you subtract one from the other one. So we'll see what that looks like here in a minute. So for the disc method, it all boils down to finding out what the area is. And so it's always going to be pi times the integral of whatever the radius is squared, and the radius itself is going to be some function of x. So it all boils down to, can you figure out what the radius is? Now, if I would have done the same problem, let's do the same exact problem, but let's do it rotated around the y-axis. So same problem. But I want want to take this area here, and I want to rotate it around the y-axis. So in this case, I know it's going to be integral dy. So I need my area to be a function of y. So then, of course, the way I've got it written over there, y equals square root of x. I need to turn that around. So x equals y squared. Right. You do have to be a little careful about where you are. There's some tricks because it's a rotation. It almost, if this would have been back here, you could have just treated it like it goes over there because the rotation would pick it up anyway. I don't know if any of you guys followed what I was just saying. So you do have to be a little careful about when you transfer from one to the other form, if it's not a one-to-one function. But this is all positive, so I'm good to go. So what's my area going to be? And where am I going to go from to? Y, of course, also goes from 0 to 1. So you always, the minute you figure out what variable you're doing, dx, dy, you desperately keep your mind thinking that variable. What does that variable do? I need a function of that variable. Everything's got to be about that variable. So it still goes from 0 to 1. My area is going to be, what's,
R squared.
and what's r?
Y squared.
Y squared. So for any given y, the radius is y squared. So this has got to be y squared squared. I love it. Cool. Right? Not that evil. So then, just cutting to the chase here, you get pi y4, so it'll be y5 over 5. 0 to 1, so it'll be pi fifth. Which kind of makes sense. This definitely is skinnier. If I look at just this side, it's skinnier. So I think that the rotation of it would end up with a smaller volume. So it makes sense it's pi over 5 versus pi over 2. Okay, maybe. So let's try some discs, some washers out. So when I first learned this stuff, I have to be really honest with you guys, I sucked at it because I hated the way it was presented. It didn't make a lot of sense to me. Yeah.
For the last step there, you just did big F of 1 minus big F of 0, but big F of 0 is 0, so it's really just big F of 1.
Good.
That works so fast on that one?
Yes, exactly. But be real careful about, if you have e's in there,
In this
then the
case,
0 won't come out 0. Yeah. But this is just
in this case, 0 is 0. So.
0, 0. So a washer. So I was saying I didn't like this because it sounded like there's a ton of stuff to memorize when actually washers are just 2 discs subtracted. So what is this thing going to look like? And hopefully I think they have one that they actually rotate on there. If I had, let's say, let me give myself an example area. Yeah, let's do that. That's fine. Y equals square root of x, y equals x. So one key thing here that I kind of glossed over is either they're going to tell you exactly all the boundaries, or they're just going to say rotate the region between those functions. So of course, how do I find out what's between those functions? Is I find out where they meet. And then they're going to be the middle of that. So of course, those 2 functions meet at what points? Or another way to say it is, when does the square root of x equal to x? 0 and 1. So that's going to be the 2 points. It's going to meet at 0, and then they're going to meet back again at 1. Right, so from 0 to 1. Of course, the x is going to just take a straight line approach. And the square root of x, does anybody know if it's below or above?
I'll go with those a little bit.
I like it below. Good guess. When you square something less than 1, it's going to get smaller. So it's always any x cubed would be even dipping lower than that. X to the 100th power almost looks like a flat line and then suddenly jumps up. Okay, so there's my region that I'm talking about, right? So now I can rotate it around X or Y axis, or I can even rotate it around like Y equals -3 or something crazy. I'm not going to do that quite yet. So let's say I want to rotate this around the X axis first. So if you were to rotate this thing around, pretend like that wasn't there. It would be this cone, wouldn't it? It would just be a cone if I rotate this thing around. So let me think, I'm trying to think of a good way for you guys to do this in general. So if I put the mirror image of this down here, that's the most I might have to do. In fact, once you do a few of these, you hopefully don't have to do any of this at all. What's my outer radius and what's my inner radius? What's the radius from the center to the outside and the radius from the center to the inside?
Outside X.
Let me see if they have a... They might have one here. There we go. This is almost exactly what we got. What did I just do? This is what I'm doing in my head, actually. You guys should have yelled at me. Square root of X is the exact opposite of what I was just saying. Square root's like this. When you square root something, it's going to get bigger between 0 and 1. That's my bad. Alright, that's the image I had in my brain. Because I was trying to not do that one because I knew it was going to come up later. So the inner radius is going to be here, and the outer radius is going to be there. Which way are they rotating this? Good, x-axis. So if I rotate this bad boy around, if I look inside, this thing is actually hollow because of the fact, so we can stop it right there. What's a good way to look at this? This is solid here, this piece. As it rotates, it's solid here, but then it's hollow in the middle. That's why it's called the washer method. Any cross section is going to have, circle on the outside, thick part, and then the inside is going to be hollow. So that's why this is called the washer method. But it's really no different than the disk method. It's just doing like that wasn't there, and it's subtracting what this one would be. So in general, this guy would be, the volume would be the integral of pi times the outer radius squared minus the inner radius squared. I want to take that area minus that area. So I just cut out the middle chunk. It's like a 3D cookie cutter problem. And of course, it's going to be, in this case, it'll be dx. So now this all boils down to then, what is my outer radius and what's my inner radius? So now that I've got everything on the correct side, what's my inner radius going to be? X. Cool. And I want it in a function of x because I'm doing dx. And my outer radius? Root x. So then the volume is going to be pi integral x squared minus x dx. And then you just go from there. From what to what? 0 to 1. Because we figured out that's where they meet. But everything is determined by what you see in the first quadrant in this case. By what you saw just from the area that they gave you to rotate. So here I get integral of that. I'm going to do this real quick. X cubed over 3 minus x squared over 2 from 0 to 1. So you get 1/3 minus 1/2 is, do I get negative area? I love volume. I love when I do that.
I think outside should be root x and inside should be x.
Yeah, the outside should be root x. Did I say the other way around? Jeff, where are you at today, man? So this should be like that. Thank you. I think I said it and then I wrote it the wrong way. So the outside radius goes to square root, and the inside radius goes to x. Cool. And it's kind of a giveaway when you get to the point where you get negative area, negative volume. You're thinking maybe I switch those around. Again, it's not impossible to get negative volume, but it normally means you've rotated something inside of itself or something really strange. Like if I try to rotate around this angle, this line here would kind of erase part of itself. Like it's a little weird. So here I get 3/6 minus 2/6. I get pi over 6 for that volume. So we did earlier the square root of x. Before we did this one, we did this, and we rotated it, and we got, can't remember now what we got for that. But what we just did was, we took that answer and we subtracted what we get if we rotated that piece around. We just subtracted that inside out. Cool. So I think we're at a good point where I don't want you to do any integration on these, because it's all about finding the radii. You should be able to do the first 3 on here. The last 3 are rotations about lines that are not axes. So that's where it gets a little weird. So what I want you to do, there's no real instructions on this thing. I don't want you to do any integration yet. We're going to do the integrals next. What I want you to do is just identify what the radii are. Identify the inner radius, the outer radius. If there are inner radii, outer radii. So the first one, is that going to have 2 radii or just 1? 1. Yeah, so this is going to be truly a disk method. And names of things don't matter to me nearly as much as process. So I don't care if you know it's a disk or washer. And in the next section, we're going to learn cylindrical shells. So I don't care if you forget the name of it, as long as you know how to identify and do it. So the first thing I do is graph this thing. I want to do this one with you guys now, because then I want to do this one and show how it's different. Because you'll see I'm rotating it about some freaky line. So here y equals x squared, and x equals 2. Where are they going to meet? 4. Yeah, so I've got, here's x, let's use a big old, let's make this, well, let's just do this, 2, 4, and so here's the x squared, and there's x equals 2. And I'm kind of implying that it's also the x-axis there.
So does that y always stop where they meet?
Yes.
In this sense?
Yes. So unless they say otherwise, you just find where they meet and do the inside.
Up to
right?
the x that they're giving.
It's possible they could say it meets and then go forward from there. We could actually do that, but normally we just do between where they meet. And in this case, I really should have probably said bounded by the x-axis, but it's sort of implied here, hopefully. So the region I'm talking about is this region here. If I wanted this region in here, how would I have to identify that? I would have to say y equals x squared and the y-axis and y equals 4 to kind of identify this region. Do you guys see what I'm saying? Okay, good. And I want to rotate this about the x-axis. Thank God I don't have to draw the 3D in. But you should be able to tell what the radius is going to be. If you need to, you can draw like the mirror image part down here. But the radius pretty much is that. So for any arbitrary x, the radius is going to be, for this one, x squared. You got to love it. I'm doing it about the x-axis. I want everything in terms of x, so I can leave that just like that. Yes?
So let's say you try to do the washer method on this. Wouldn't 2 just become 0 when you try to do the radius? So that way it just forces you to do the disk? Or not?
Do a more time for me.
So let's say I attempted to do this as a washer. Like in the equation, when it just dropped out, it forced me to do the disk because of turning the 2 into a 0.
Because there's no like other function in here that has a distance between itself and the x-axis.
Okay, so
the other function really is the x-axis itself, which is 0 distance away from itself. So that's that. Now watch what happens if I do this. So I've got the same setup. I've got my 2, I've got my 4. They meet there. There's that. So that's the region I'm still talking about. But now I want to rotate it about y equals negative 2. So just for the purposes of this, don't do this yourself. But that's 2 away, even though you could probably do it better than I'm going to try to do it right now. So that's roughly the mirror image, right? Looks like some giant beast is coming up over the mountain. Let me get out of there. You guys kind of with me? So if I rotated this, it would end up over there. So this whole middle region would be empty. You with me? So now it's kind of easy. Here's my middle line. So my radius is going to be defined like this. My radii are like that. So I really didn't need this other piece, but I just put that in there. I don't know if it helped anybody. But just to see what this thing would look like if I rotated about y equals negative 2. There's my radii. They're just in relation to negative 2 now. So what is this outer radius going to be?
Square root of y? Y plus 2?
The outer radius, not the inner radius.
Oh, I'm sorry.
So you were correct. The outer radius is always 4. You can kind of check it. At this y, the radius is 4. It's always 4 away, right? Because that's a straight line down. This is the one that's going to have some functional dependence on. In fact, in this case, what do I have to have everything in terms of?
Y.
Y. Good. So I'm given y equals x squared, which means that x equals square root of y, which is good. I don't have to worry about any weirdness because everything's positive to begin with, so I'm good there. So this inner radius is going to be, you can always do this, square root of y minus negative 2. So just square root of y plus 2. Right? It's going to be this distance. You guys kind of with me? That distance is the square root of y. Is that cool? Because that's how far away this function gets. That's the definition of it, is the output tells me how far away I am. It's the height that we used way back when. Plus this 2, just to get to the midpoint, the midline. So there's my inner radius. So what would this interval look like? I know I just said we wouldn't do it, but I want to do it anyway since it's right here. What would this interval look like? And this is where people, and again, I can't stress this enough, you do not have to worry about the line of rotation or any of that when you're setting your interval up. Your interval is all about that original region. Everything else doesn't actually happen. It's just the math mimics it happening. Again, I don't know if that makes any sense right now. I don't actually have to rotate anything. I don't have to do any of that in my mathematics. It's the math process mimics what would happen if I actually did rotate that thing. So everything's based on this. And it's got to be dy like we just said. So what's y do?
Y. I'm going to do pi square root of y plus 2 squared.
Don't go there yet. I'm not talking about the inside yet. I'm just talking about the limits.
I'm sorry.
So what does y do?
0 to 4.
0 to 4. So then the inside is going to be, I can put the pi on the outside pretty much as it's a constant. So it's going to be the outer radius squared, that's 16, minus the inner radius squared. Let you guys absorb that for a second. How do we feel about this so far? I mean, this is... Some of you guys look like you want to hurt me. Hopefully that's not true. We'll find out later, I guess, if you meet me in the parking lot. Do what it means. Alright. So we're going to do a few more of these, obviously. And hopefully, I know it's a little early to say this, but that should be something you could work on. It should be the easy part of this. Actually doing this interval. Right, just FOIL that bad boy out. It's just a bunch of y to a power. That's easy to integrate, and then you just plug numbers in. That should be the easy step. Go ahead and try to do this one. So that should be the region you're working with. This is the x squared, and this is the 2x. So this is a lot like the one we did there, except it's actually the one that I had in my head when we did that one. So for the 2x. How would you set that? What would the radii be? Do you have those? So be careful now. The outer one would be from the midpoint to the farthest side, right? So when I'm going around, whatever axis I'm going around, the radius is going to be the distance from that line, the outside radius to the outside, and then the inner one would be the one that's closer. So the outer radius is just going to be 2x, because that's the further side, and the inner radius is just going to be x squared. That's the closer side. So in here, this chunk is going to be solid. It's going to be rotated around. And it's going to end up having some empty area in the middle. It's going to be a really strange looking glass. It can hold water, but it's very strange. And I don't really leave much room on here for integrals. But what would that integral look like? It's going to be dx, because we're going around the x-axis. Anything parallel to the x-axis, dx. Parallel y-axis, dy. What does x do? And it's so stupid easy to put 0 to 4 there. Especially if you just did a bunch of y-axis stuff and then you just look in the wrong place. But again, keep telling your mind, no, it's all about x. And then what do I put in here? The pi can go out there. And here's going to be... Good, so 4x squared minus x to the 4th. Cool. And then, again, that should be the easy part now, finishing that out. Right? I know integrals are still kind of new, but they're just opposite of differentiation, so it should be not too bad. Now it's the same thing except around the y-axis. All right, so I think that shouldn't be too bad. What I want to try is this guy. Go ahead and try to do this guy. Graph those. See what it looks like. Whoa. You guys probably already noticed this, but somebody stole our clock. Just make sure everybody's on the right track. What's the first thing you all should be doing? Even before I graph this, I would... Yeah, I want to see where these things meet. Right? And before you graph it, you want to have an idea where these things meet, because that'll be nice. You can plot those points directly, and then that kind of helps you fill in the shapes on top. Plus, you don't draw too much and get too much in there to throw you off. So how do I find out where these two things meet? So it means really just crazy. So I say that x has to equal the other x. Or y squared minus y minus 2 has to be 0. Cool. So then... I like big ones negative, make that negative. So they meet at y equals -1 and y equals 2. When y is -1, x is what? Either one should be the same, right? So where they meet. So when y is -1, x is -1, looks like. So see, when y is -1, x is -1, sure. Sweet. So when y is -1, x is -1. When y is 2, x is... No. -4, yeah. Good. A bunch of negatives in this problem, so you gotta watch out. So now, I use that information. I know that they meet at the points -1, -1. And I got lucky there. You gotta be careful. X, Y, right? So then they also meet at the point -4, 2. Now, you guys probably... you should certainly be able to handle parabolas that open the other way. Right? Instead of up, down, they open left, right. And, I mean, this one hasn't been shifted at all, so none of the vertex is going to be where?
0,
0, 0. So these points, actually, you should be able to see that they give me the shape of it already. So there wasn't too much work involved there. Because they know it's still at 0, 0. It's a negative y-squared, so it's got to open the backwards way, right? And then the line pretty much has to go where? And you can kind of double check, but yeah, I already know where this meets. And that's why it's so much better to first find out where they meet before you try to start graphing them, because there's less work involved if you find it. So it's got to be here. And just to make sure, it looks like it's got a x-intercept at -2. So when x is -2, sure enough, y is 0. Is that cool? Okay. So this is the region that we're talking about. And now on top of that being a weird-ass region, we are rotating at about x = 2. So let me give you guys a couple minutes here to figure out the inner and outer radius.